Hi, welcome to my tea time talk. I'm going to present my work on co-agent networks, and which boils down to structural graded assignment in neural networks using reinforcement learning. This is a joint work in collaboration with Geber, Matthew, James, Phil Thomas, and Martha. So a recap from Martha's talk. She gave us a basic structure about how you will formulate the neural network graded assignment problem into a fixed horizon, finite horizon markup decision process, where at the first step you see an observation, and at each step each layer acts as a policy, an RL agent policy, which outputs an action, and that action goes on to be observation for the next agent. And the trajectory looks like this, where the reward at the intermediate steps is 0, and the final reward and the return is going to be the loss function, the negative of the loss function. And this the way, like, if you separate the policies out for each layer, we can write the policy gradient of, like, the objective of the policy gradient with respect to the parameters as the individual gradients of each layer, and which corresponds to the reinforce update. In this talk, I'm just going to present some results and show the failure cases of the reinforce update, and like in the on policy setting, and the fact that nondeterminism is the basic problem in training these networks. So for this experiment, we're trying to keep the networks as similar to Backprop. So for that, we have a Gaussian parameterization for each node, where the agent outputs the mean of the Gaussian. We use a fixed gamma for the whole network, and we have let's say k number of layers and n number of nodes. We try on two data sets, MNIST and Boston housing. For the MNIST one, we use a reward of minus cross entropy loss. And for Boston housing, because it's a regression data set, we use a negative mean squared error loss. And in these experiments, the agents are linear functions. And even though we're treating each layer as an agent in this case, because it's a linear function, the parameters for each node in the linear function is also disjoint. And in a sense, it looks like an observation is coming into a co-agent. It's linearly weighted and produces a mean, mu. From there, we sample a pre-activation Z, and we pass it through a ReLU activation to get an action for the agent. Now, the standard reinforce update is claimed to be very high variance, and it is high variance. So we also try to use some baselines to center the return update, and probably have a little low variance update. And we adopt 4 baselines for that. Not 4 baselines, 4 algorithms for that. The first one is the reinforce, which is the standard one. And in this case, we don't average out any of the nodes in the graph. This is how a graph would look for the whole learning process, where X and Y, X is the input for your learning method, and Y is the regression target or the class target. That deterministically becomes an observation, and followed by theta 0, which gives you the first action. We deterministically move to the next observation, and so on and so forth until we produce k plus 1 actions, and terminate the episode with the final reward. And let's say we'll talk about the second layer in this case to show the different baselines that we're using. So the first baseline is a global baseline, where we just have a moving average of the past returns. And this, in a sense, means averaging out the return of the previous seen observations. The second one is a state global baseline, in which we estimate a value function for the input to the current to the whole neural network, or the whole co-agent network, which essentially means averaging out the estimating the return for a current input or observation, which is Vx. The fourth one is estimating a layer-wise baseline for each observation each layer observes, which for the second agent means estimating a value function for the observation it sees. And this is how the update would look like for that. Now, in this experiment, we compare against Backprop, because Backprop has continuous activations and the same structure like with the ReLU activations. The MNIST classification is run for 50 epochs, and the regression is for 10k epochs. We tried on 1 and 2 layer neural networks, and we have 10 seeds. Yeah, so the first row shows the results for MNIST, and the second row shows the results for Boston housing. Higher is better in the case of MNIST because it's accuracy, and lower is better in case of Boston housing because it's a loss. The thing that we observe from these results is, although the baselines help, but having a more local baseline is not be significantly helping in the learning performance. As you can see, like the reinforced update is higher variance in the case of two-layer network, and having a global baseline or a state baseline does help, but there is no specific difference between each of those baselines as such.
Hey, Dhawal, I have a question about this experiment. Your agent has stochastic nodes, but you're comparing against Backprop.
Yeah.
That seems like there's a difference there.
Oh, yeah. So when we are evaluating an agent after it has been trained, we evaluate the agent based on its greedy policy. So when we are calculating the accuracy or the loss, at that point of time, we are not sampling any actions. We are just taking the greedy policy of the agent, and that gives us a deterministic output for an input. And that's what we compare to Backprop. Is that what you were asking?
Yep.
Yeah. So moving on to the problem of non-determinism, like why is this gap there between Backprop and coagents? So to figure it out, we first see if we pre-train the coagent solution with Backprop and then you switch to a coagent learning algorithm, what happens? This is tried on two-layer networks. And in this case, we train the network with Backprop up to 5K epochs. And then from there on, we switch to a coagent learning algorithm. And this over here, we train the first layer of the network. And the different lines shows the ratio of nodes that are being trained. 60, like each layer is 64 nodes wide. And we can observe as we almost cross the half threshold for the number of coagents being trained, we see a sudden degradation in the performance, which kind of points to the fact that it's very difficult for the agents to determine the non-determinism in the other set of coagents is difficult for, makes it difficult for the agent to figure out what action is good. And the other thing we tried was a partitioning scheme. So in the current scheme, each layer is a stochastic layer. What happens if we have a mix of, let's say, stochastic and deterministic layers, where, let's say, a C3 network is basically a two-layer neural network with the last layer being stochastic, or the last activation being stochastic. C2, C1 would simply mean that we have a single layer neural network which is stochastic, followed by a linear layer which is stochastic. And C1, C1, C1 is the standard network in which all the three layers, all the layers are linear and they're stochastic. And what we observe is, if we have the last layer stochastic and we still use Backprop, the C3 layer is able to achieve the performance of Backprop. Whereas as we increase the stochasticity, as we increase the number of stochastic subnodes or nodes in the network, the performance starts to become worse, or approaches the performance that we see with the normal coagent. Yeah, so this hints to the fact that the non-determinism in the other coagents is kind of hindering the performance, and it's making it difficult for one node to figure out how much impact its action is making. Now, one way to deal with this is in RL, we usually decay the exploration parameter. In all these experiments that we did, the sigma was fixed. We didn't decay it. So what happens if you try to converge the network to a deterministic policy? Will the performance increase? Will it match Backprop or not? So there are two ways which you can do this. In one way, we can either learn the sigma parameter, so we tried this by using a bias unit for each node. And the second way is to just globally decay the sigma parameter for all the coagents together. And the results were not we found out that this doesn't help. So in the left graph, you will see a learned sigma parameter where the different activations tell you how the sigma parameter was activated, because we need a positive sigma value. So we pass the bias unit through a sigmoid exponential ReLU, and the fixed one is the standard one. And all of these are initialized with the best value we found in the last experiments. And like it seems like learning the sigma parameter is not helping. And similarly, if you're decaying the sigma parameter, the performance also seems to often diverge, which can be because if you're decaying sigma too fast, and if the agent is sampling an action which is out of the distribution, the update becomes so large that it might interfere with the past updates and like wash away all the learning from the past, because the gradients are so big for a smaller sigma value. Okay, yeah, and this basically comes down to on-policy failure, like how on-policy learning is failing in this case. Now, this sigma value, like controlling the sigma value, is particularly hard in continuous nodes, and switching to discrete or binary nodes using softmax activations gives a natural way of controlling the exploration parameter. And for this case, we have like, it's a similar cohesion, but we've changed the parameterization of the policy. We have two actions, discrete actions. We pass them through a softmax, we get a probability of those actions, and we sample those actions. And one action corresponds to a 0, and the other action corresponds to a value of 1. We have the similar baselines, like we experiment with similar baselines, and we also have a Monte Carlo value function based method for 50 epochs and 1 and 2 layers. Over here, because we don't have a direct corresponding to backprop, we use a straight through estimator to compare. And a straight through estimator basically passes the gradients from the upstream nodes to the downstream nodes if the activation was 1, or if the activation was 0, it doesn't pass on the gradients. And like there is some theory around why it doesn't work for 2-layer networks because of misalignment. So, and we can observe that actually happens in this case too. The interesting thing is this binary network works better than the continuous network. And we observe and in this case, we can also measure the entropy or the exploration of the binary nodes easily. So the last experiment was for 50 epochs, and we run the experiment for longer time. And in this case, it's 10 key epochs for 3-layer networks. And we do observe that the binary nodes is able to achieve an accuracy of 99% for training data sets, sorry. And over here in this graph, we have, well, there are a lot of lines. So the red, green, and blue solid lines correspond to the entropy of each, the mean entropy of the whole layer over the learning schedule. And the dotted lines corresponds to the sparsity of the learned representations. And what we observe is the layer 1 goes on in entropy very fast, and layer 2 and layer 3 decrease in entropy. And as in when they decrease in entropy, we see a sudden rise in accuracy. And from there onwards, the entropy starts to creep up again, but the accuracy still keeps on increasing, which again points out to the fact that the agents are trying to figure out the non-determinism between other agents, but they have settled down to a good enough policy, and it's not changing a lot. And like sparsity.
Dhawal, I think some of these arrows don't exactly point to lines. So can you tell me which of these lines are sparsity and which of these are entropy?
The dotted lines are the sparsity, and the color corresponds to the layer number.
Okay.
And the solid lines, the colored solid lines are the entropy.
Okay.
And so we did try a couple of experiments to figure out why this is happening. And we tried to change the representation size to see if having a larger representation makes the policy more deterministic. And we did find that it does that. But we wanted to see why a 64 node one is not able to become a deterministic policy. Which, so we should, we move on to the off policy setting where we tried start estimating critics now. And we update the critics using 2 updates, the SARS update and the Q-learning update. Now, one point over here is in the SARSA update, you can learn the critics with a single forward inference, but in the Q-learning update, you need to have a max over the critic of the next coagent. And having a max over the joint action space of the critics over here is a layer critic. So the input is the observation to that layer and the joint action to that layer, like the joint action that layer takes. So maximization over that is infeasible. So as a proxy to that, we sample a greedy action from the next layer. And we use that as a proxy for a greedy value, which is not a very sane way, but it's one of the ways to do it. And we do observe that having an off-policy critic can help in the performance, but it is important to know that both of these performing curves are worse than the reinforced performance in this setting, which is kind of sad, but at least we are able to see that off-policy learning is helping. And I have a new result, which in the reinforced setting, when we use a critic, when we use a off-policy update, it does seem to help in the initial learning. And when we measure the entropy for this case, we do observe that the entropy for the layer 2 goes down, but the entropy for layer 3 still not as high as the earlier one, but is still pretty high, which can be because the layer 3 is not learning from is not learning a critic exactly. It's still bootstrapping off of the actual return.
Is this graph is smoother than the previous one? Am I supposed to notice that?
Yeah.
Is that like a result?
Yeah, this is smoother.
Okay.
It's because the learning is happening using critics over here rather than the full return or the actual observed return.
Well, is the SARSA one just as smooth?
Yeah. And I just skipped. So this experiment was a way to show active exploration that stochastic nodes can offer. And we had two sets of problems. And I only have 2 minutes, so I'll just breeze over this. And in this case, we compared them with standard optimization procedures like Adams, RMS prop and GD, gradient descent. And we did find that stochastic nodes can help. And the advantage of stochastic nodes is that they offer a way to do active exploration rather than compared to passive exploration, which happens in stochastic gradient descent, which becomes a property of the dataset rather than the property of the agent. And we also tried this on a container learning problem where we have a regression problem with a single input and a single output. And D is a parameter which controls the level of difficulty of the problem. D is equal to 0 is an IID data. And as we increase D, the correlation between samples increases, but the end distribution is still coming from a stationary, an IID distribution. And for D is equal to 0, as expected, Backprop will outperform cohesion networks. But for higher values of D near 1, we do observe that the cohesion networks are able to perform much better than Backprop. And the sensitivity to learning rate is also much less when compared to Backprop, which can be attributed to having a good amount of exploration. And yeah, this is like the final, this I just got today. So this is like with the reinforce and doing off-policy learning on the remaining network. So there is some initial performance increase, and I still have to do a little more understanding of what we can do to improve this further. Yeah. Okay. I think, yeah, I finished on time, hopefully.
I have a question. So we've seen a couple talks this summer about, I'll just call alternatives to Backprop or the standard way of doing things. And it's tough, right? Because it's, I don't know how many decades of development of one approach and an army of people with giant computers versus a couple people here. What do we think is like the best place where we can show good results so that people start getting excited about this? Like where is the low-hanging fruit here, or the experiment that we should try to convince the world? And this is kind of open to anyone who's been working in this area.
Yeah, like this is something which we're trying to figure out. Backprop is meant to beat, is meant to overcome problems of where you have a very smooth direction of update and there is no continual learning, and a place where things change, keep changing, and we need a functional proximity to adopt to that. That is a place where we can hope and a learning method which have some kind of exploration, active exploration will help us. So like the continual learning problem, or non-standard network architectures also. Like Backprop has access to the information of the whole network, the structure of the whole network. It's like it has a model of the whole network. What happens if you have distributed models throughout your system, and like having an experiment which compares incomplete information about the model will kind of, I think, bring out the positives or like advantages of using these methods.
So why does Backprop has the model of the whole network?
Backprop uses the exact gradient information of each node, right? It needs the upstream gradients from each node.
So
down.
You can actually implement Backprop by just looking at the neurons ahead of you and those behind you. That's it. Just propagating local information is, you can implement Backprop in feed-forward networks at least.
But that's not Backprop anymore, right? It's not.
No, you can do it Backprop. It would be the exact gradient. In fact, that's exactly what Backprop does. It only looks at, so every neuron would only look at the immediately local information from forward, from the next neuron for backward pass, and then previous neuron for the forward pass.
So that local information will be available only after that neuron calculates its gradients, which is the local information from the future neurons, right? Or the upstream neurons.
So okay, let me put it this way.
Immediately.
Your first layer neurons do not know how many layers are in the network, and they do not have to know how many layers are in the network.
Yeah, but it has to wait for the upstream neuron to calculate its gradient with respect to its upstream neurons, right?
So there are ways around that as well. So there is something called pipeline backprop, and then I have another version which is a generalization of that. So you can even compute gradients even without that restriction. So just saying it, but I agree that it's not doing continual learning as another limitation.
Well, they're not exact gradients.
They are exact if you don't update, right? So if you update, then you have stale gradients. But if you don't update, then they are exact gradient. They're just delayed by a certain number of transmits.
What is it called?
Sorry?
What is this called? Method?
So I think the one that's published is called pipeline backprop. So they implement it in a way that you don't have to wait and everyone is processing. And my version, I call it real-time networks, but it's still like just a different implementation of the same idea.
It sounds a lot like real-time recurrent learning if you're like updating on every step when you're calculating the gradient, like similar to that.
But it is different. So real-time recurrent learning is the forward view differentiation, but it's not that. It's still doing the differentiation in the same direction, starting from the output going back. But it is similar, and the stale gradient aspect is similar. Yeah.
So I think Adam's question is really related to the conversation we had during Kenny's talk as well, right? Like we had this talk about stochastic networks and when would having stochasticity in the network be useful? I don't know. That still seems like an open question for our lab group. At least it is to me. I haven't thought about it though. So
stochasticity, which is controlled by the agent, is helpful, I think, rather than being a feature of the environment or like something which the environment forces upon you to do. It's better that the agent is stochastic, and that gives it more control.
I think what I was saying is like, what domain would the agent having stochasticity in its representation would we see benefit, right? Like I think that's the core question with this style of network.
Yeah.
I guess what I'm directly thinking of, there's several people exploring different algorithmic approaches, and that's good. I wouldn't want to merge those, but maybe there could be an agreement on some test problems that people use together to explore the space. Like Rich just talked about C-suite for continual learning. It would be useful if there was a shared set of problems that all the people working in this area trying to promote alternatives to Backprop could use. and share their experiences and their learnings.
I have a question. Like, can we use this this way that you kind of implemented a stochasticity in your network to measure the uncertainty of the network? I mean, uncertainty in the weights or updates.
Like how frequently the weights are changing, or like if the direction of the gradients are changing, like the variance of the gradients?
No. Something like Bayesian network, something that like, can you kind of know the like variance of the each weight or something like that?
Oh, I think you're talking about variance in the predictions, like for a given input, how much my output will vary.
Yeah, one of them is that, but another one is that, like, you know, the variance of each weight. Like, do you have a mean or variance for each weight or something like this in your network?
I'm not sure. Like,
so maybe are you saying the error in the estimate from the optimal weight, something like that?
Yeah, something like that.
Given that I've seen a different stream of data, either the data itself is different or I saw it in a different ordering, I could end up with different neural networks, different sets of weights. What is the variance in that? That would be, say, the posterior from a Bayesian perspective.
Oh, okay. Yeah, I haven't looked into that. But so, like, would you compare that to something of what like a backprop version achieves, like the variance in the weights that a final backprop solution has?
Not backprop, but like, you know, other learning techniques like for like Bayesian neural networks kind of can measure the uncertainty in the weights. And I was wondering if that happens, then you can actually use this information for exploration if you use it like in reinforcement learning or something.
Yeah, like you can definitely employ techniques from exploration in RL to this, and it's just a start. Like this is just an introduction to that. We have the whole RL literature to apply it to if you want to in this case, and we plan to do that at some point of time, and let's see what happens if we have experienced replay buffer, which like, yeah, we can try a lot of things on this now.
I'd like to build on that question a little bit. I mean, I'm curious about the relationship with dropout and backprop as another way to encode stochasticity within the network. And I think it's actually very related to Irfan's question, because backprop, doing Monte Carlo samples through backprop, so given a single input to my network, I can sample multiple outputs from my now stochastic network, and that can be seen as an approximation to this sort of Bayesian network, like Irfan was asking. Do you know, is there any sort of relationship with dropout and your proposed stochastic networks? Any similar views on like modeling this uncertain parametric uncertainty?
Yeah, so the way I look at this is, at least for the discrete or binary case, it's like a adaptive backprop where the adaptive dropout, where the dropout is state dependent at each layer. And it does something like that. And there's another variant where you can have this dropout learned for a neural network, and then you do dropout, you'll do a learned dropout from this network on an actual neural network, and then you do the standard based on that neural network. That's the closest thing I can think about in terms of backprop, dropout, sorry, not backprop. Yeah, Rich.
I don't know. I guess this is a comment because, so if I can say what I didn't hear you said, maybe you said at the very beginning, you guys are exploring this, what you can do with networks of stochastic reinforcement learning agents. That seems to be the topic. And so it's a sort of a solution-oriented research program. You know, it's like guys who study genetic algorithms, they say, oh, I'm really like genetic algorithms, so I'm going to look for a case where they're good or try to show they're good. And actually neural networks was this way a long time ago. You know, they would they would, people would be fascinated by these neural metaphors, and they would try to find places where it could be good. So it's like solution method oriented research rather than problem oriented research, right? You're not take some problem and say, I'm trying to solve it. You're saying, I really think this kind of solution method has something to offer. I'm going to study it, and maybe later I'll find something it's good for. So this is a risky strategy. I think I always advise people that they should start with a problem and be driven by a problem. Be driven by a solution is risky because you can't say what it's good for. And so it'd be good if we had some statements up front what it might be good for, and then we take those seriously. Okay, now the other thing I want to say is, like, this particular strategy is also very familiar to me. Networks of stochastic units. This is like from the earliest days in the 80s. Okay, this was a thing, and my advisor, my supervisor, Andy Bartow, he was really into it, and we never found anything that was good for. I guess that's what I'm thinking, and but maybe it'll be like neural networks. Maybe we didn't find really good things for neural networks, and now it's it. It can work out when you do a solution-oriented research, but it's kind of risky. I'm always looking for a way that it's doing something better than other ideas. That's a comment.
Yeah, I kind of agree with that comment too. It's a little bit solution-based approach, but the motivation of it didn't come from a solution-based approach. The motivation came from how to do asynchronous and decentralized learning. And once we started looking into that problem, we found that we can formulate this stochastic network into a finite horizon problem, and then that took a turn into finding if this way of framing the problem can help in credit assignment. And because this framework does allow you to do asynchronous learning and decentralized learning too. But yeah, this can be risky. I agree. Martha.
Yeah, I was gonna, nicely said that, Dhawal. I agree. Our problem setting was mainly to think about how can we learn in asynchronous problem settings. And then we are not testing in those settings. We instead are motivated by them and say, well, let's step back to the easiest setting and first understand how the algorithms behave here. That may even be a bad idea. Maybe we should be tackling right away the setting we care about. But nonetheless, it's the one that we did. I was just thinking about what you guys were saying about when is this better than Backprop, or like what are these methods good for? And maybe I'm thinking a little bit about, we took the RL route mostly because we didn't know how else to solve the problem. So like Dhawal said, we want to be able to train these networks. We assume we have asynchronous inputs and so on. And we naturally just gravitated towards using RL for each node because it was our only solution strategy. But like Kerm's saying, other people have thought of ways to do local updating with Backprop, where you just do, like, you might have to wait or you'll use stale gradients, but it is a different strategy. And I almost wonder if we're back to the same question we usually have about, should we use gradient descent or should we use black box optimizers like RL? And in some sense, we went to the black box optimizers and said, we're not going to use this nice local search strategy that is gradient descent. It's no longer as perfect because it's approximate stale gradients, but nonetheless, it's a reasonable choice. And then otherwise, black box optimizers have their own advantages, like they're less likely to get stuck in local minima. Maybe they can build models and more globally search the space. So I would say that I don't know which of these two strategies will be better, but both gradient descent and black box optimizers continue to be used. Maybe that's the only difference. Maybe Khurram's new extension on pipeline Backprop is exactly just as applicable to any kind of asynchronous setting. It's perfectly decentralized. It just uses local information that slowly propagates its way backwards. So maybe the only distinction is gradient descent versus RL. Versus black box optimization.
Maybe there's one more difference. That it's decentralized, but it's not truly asynchronous. The one that my version, it's still assuming that you have some clock so that everyone does the same amount of computation per time step. And maybe, I think here you don't even have that assumption, right?
I guess that's good enough though, maybe, but fair enough. Good point.
But if the goal is distributed, I think, and that is, I think, the goal, then that version works.
Okay, Chab is telling me that this is the wrong categorization of algorithms. So you're gonna tell us more, Chab?
Sure. I'm just surprised to hear that, like, in my mind, it was the other way around. Like, most of the other algorithms try to use more structure. So they are not black box. They're trying to use some Markov structures, some Babel equation. They are the furthest away from black box that I can think of. And gradient methods at the same time, they are kind of like based on this oracle view of the world, that an oracle gives me a gradient. I can just like follow the gradient. So that's totally black box to me. So why did you flip around these two labels?
Well, let me say how I always thought about black box. Black box to me means a function. You know nothing about that function. You can just query that function. You don't get to know the gradient or anything about it.
So that's zero order optimization.
That's right.
First order optimization. But in reinforcement learning, we don't run zero order, general zero order optimization algorithm. That would be the cross entropy method or whatever, right? We don't tend to do that. Like some people do, but that's not reinforcement learning by and large.
That's fair enough. So arguably reinforced could be seen kind of like the cross entropy method. It's using like very little structure. It gets a sample to return, it adjusts the probabilities. But then otherwise, once you start using the Markov structure, then you have now assumed something about your world. So maybe it shouldn't be called black box.
So whenever you introduce any value functions, and when was the last time that these methods would do anything without introducing value functions? There was not a single case. Is there a case where it reinforce without using value functions does something amazing? Not really.
Because right? Everyone uses baselines with reinforce. Otherwise it sucks.
Yeah.
Yeah, that's true. Yeah, that's fair. One could still argue that those are just smarter black box algorithms that they know they recognize the structure of the Markov problem, but they have to build up the value function, whereas gradient descent gets to query an oracle for that gradient. It's like a little different, but nonetheless, you're right. They both assume some structure.
Okay.
I still personally think assuming access to a gradient inside the network is a stronger assumption than that there is some kind of Markov structure.
I think gradient descent in some sense accesses the structure of the reward function also, like the loss function. And that's how it's able to update.
So there is a confusion here, I think. Going back to, okay, what problem are we solving? If you are solving a reinforcement learning problem, you can approach it with so many different algorithms. You can, like, you have some information structure of what observations you're getting back, and what interactions you have, and what is your goal. And then from that, you can choose a solution method. It can be a zeroth order method, it can be a first order method, it can be whatever, value function based method. It's, let's not mix these. Reinforcement learning is a class of problems, and then we can throw whatever methods we want to throw at it. And they can be black box methods, but reinforcement learning per se is not black box or anything. It's just a set of problems.
It's just possible that I'm not defining black box correctly here.
So I wanted to, maybe comment on this thing. So like back in the day, before we had all of these differentiation algorithms, forward and backward differentiation, MATLAB used to have like an optimized function, right? You just pass it a function and it does some gradient descent. And it didn't have access to the internal structure of the function. It just had zeroth order information. And it would recreate the gradients by numerical differentiation, right? Just perturb the inputs a little bit. And go from there, right? And that's like a systematic way of getting approximate gradients from zeroth order information. And you can do the same thing sort of stochastically, right? So if you want to find a gradient at some point, you can sort of randomly add an epsilon to that point, get your black box function. And as long as you do this for enough points, you will get an approximation to the gradient, right? And then it was considered a big advance when we got all of these TensorFlow and things like that, that could compute analytical gradients, right? But in the end, it seems like whether you're doing the 0th order information and getting fake first order information out of it, or directly getting first order information, the algorithm is basically the same, right? Like there's going to be some small difference because of numerical issues, but if your function is not terrible, it's going to do more or less the same thing, right? So I guess my question is, how do you tell the difference between an algorithm that is in spirit the gradient, just using some stochastic way of computing gradients and then following the gradient, versus an actual algorithm that is fundamentally different from a gradient algorithm?
That's a good point. Let me say maybe one other thing about the difference here is that in both of those settings, you still assumed you had a smooth function. You just didn't, the Oracle didn't give you a gradient. And I suppose a lot of black box optimization algorithms are not making such assumptions. So they wouldn't even always try to estimate the gradient because the function is not smooth. In any case, your philosophical question is, I guess you couldn't tell the difference between those two.
And I guess when you say that they're not making the assumption explicitly that it is smooth, does that mean they actually work well for non-smooth functions? Or do they just make the assumption implicitly and then just happen to work for smooth functions?
Oh, I have no idea, actually. I don't know enough about black box optimization. Thus my potential misuse of the word.
Yeah, okay. Yeah, I think that's an interesting question.
This can also be thought of as a perturbation method on the activation space in some sense. Like the one you're talking about where you do an epsilon update, that's perturbation on the weight space, right, for a network. And then you try to see the difference in the outputs and you treat that as a local gradient. And in essence, this is more like a perturbation on the activation space of each node rather than the weight space. And then that perturbation on the activation space can be turned into a gradient update.
Yeah, that makes sense because the output of every layer is the layers after that. And so if you want the gradients of the layers after the current layer, you have to perturb the outputs of the current layer, which is how you would get. Yeah, so that makes sense.
Have you thought about this method for maybe when you initially have a misspecified model or you don't have a good approximation of your MDP?
Like in this case, you're assuming that your agent at least has the information of a local MDP, like information of the next agents and the backward agents, maybe, or the access to critics in the subsequent in the next layer.
And the critics know how good the representation is?
No.
So like maybe like, let's say you do a few like online updates and then you know that after 5 or 6 episodes, your neural network is not doing a good job representing your MDP. So you don't want to learn a good solution to that MDP because for whatever, like, you know, it's bad and you want it to take into account how bad the MDP is. So if you run gradient descent, you learn a very good approximation for your misrepresented MDP, which you get stuck in kind of this poor feedback loop where your agent thinks it knows the environment and it stops trying to gather more data about the environment.
I don't understand, like the misspecification of MDP, the MDP is fixed, like it's not something.
I guess maybe what I'm saying is like let's say you have an MDP and usually we assume you're given good features of the MDP. So if you solve the featureized MDP, you have a good approximation to the optimal policy. But maybe a lot of times with neural networks, it learns a representation. The representation is not a good representation. Then what? Like, what do you do?
I'm going to have to agree with Andy for just a second here in the chat. Just to be clear, that our MDP is the neural network. The neural network isn't approximating MDPs or anything. Like, we're not approximating the true model of a MDP. We're saying a neural network is our MDP and our agent's goal is to solve that MDP.
Oh, okay. And so you just want to solve the MDP the neural network knows. You don't actually care about how good that MDP is about approximating the real world.
There is no real world. The neural network is the real world. It's a very strange thing. The agent's world is the neural network.
Okay. And Okay, maybe then. I'm not 100% sure on the setting then. Sorry.
Yes, it's reasonable. The only goal here is to train a neural network to do regression.
Okay, so you just want to minimize B minus AX.
Yeah, we want to minimize
the residual B minus. Okay, okay.
Let's say.
I have a question that might actually be related to this confusion. Maybe will help or make it worse. I'm not sure. But from the perspective of each layer is like a number of time steps away from my final reward. So the very first layer, I'm getting immediate rewards. So reinforced from that perspective is actually just like a bandit thing. It is a one-step immediate reward. From the second to last layer, then reinforces is this Monte Carlo thing that is 2 time steps deep, third to last layer, 3 time steps deep, so on and so forth. I'm curious, when you were testing baselines and talking about the variance of reinforce, I think the variance comes largely from the number of time steps out, the sort of depth of that search. And your networks, I think, were only 2 layers deep. So I'm wondering if you actually saw a lot of variance issues. I noticed the lines with the various different baselines were pretty similar. And if I was maybe a crotchety reviewer, I might even claim those are basically the same with respect to like noise in your performance estimates. I'm curious, have you tried like extremely deep networks, which is something that we know Backprop actually has some issues with, like 100 layers of 5 units each or something. I'm not good at designing architecture, so don't take this as literal advice, but in that spirit, have you tried that? And then did you see big differences in the reinforced baselines or after critic?
Yeah, I did try that, but I didn't plot them. Yeah, I remember thinking about this and like having like 4 nodes and very deep networks and actually seeing what if, because baselines could help more in that situation. 2 days is actually not enough to show this problem. Yeah.
Time to try a 100-layer neural network.
Yeah, I think I should try that. Yeah, I'll definitely try that.
Okay, I'm sure other people have to go, but this discussion reminded me about one thing that's technically another advantage, since you're talking about the differences between solving with gradient-based versus approximating the gradient with scale-like things versus using RL methods, is that there are less restrictions on the reward function at the end, like Dhawal said. You have to be able to take the gradient of the reward function for gradient-based things. Everything has to be differentiable. Technically, for all these little co-agents, it doesn't. It can be any reward function. You could directly minimize 0-1 loss, for example, if you want.
Yeah.
Not when you say reward, you mean the error?
Yeah, sorry, the error at the end. The thing at the end that the agents are optimizing. That's not clearly that important, to be honest. Which is why it was not our problem motivation. The asynchronous thing was.
I actually had a question that was maybe almost the opposite of what you just said, was that because your reward has some like known structure, for instance, in the regression problem, it's a quadratic reward. I wonder if you could take advantage of like an LQR like solution to find your weights, taking advantage of the fact that that was a quadratic reward function.
Not sure. How do you do that in RL? Like, does the LQR solution actually leverage the structure of reward usually?
Right. I don't know a lot of the details. Yeah, actually, I'm just going to stop there. I don't know a lot of the details. I wouldn't be able to help you live right now.
Yeah, but definitely, if you have the structure of reward, then gradient descent can use that issue, can use that information very well. Like if you have the exact reward function, then that's best. This essentially is just trying to correlate the return with the action that the network is taking.